Okay, so the question is about the arc-length formulas. In one case, there's a 1 plus whatever, but now when we're looking at um, higher dimensional type stuff and multivariable things, that constant's no longer there, right? So if we think about where this arc-length formula comes from, let's say we have some kind of function, right? And we want to know the length of that function in between these 2 points. Okay? So we want to know the length of that curve. Okay? And we start off with a real basic idea of the Pythagorean theorem. How far do we go over? How far do we go up? And then we know the sum of those squares is equal to the square of this, right? Now, imagine then that this is the change in the x-coordinate, so we're going to call that delta x, and this is the change in the y-coordinate, so we call that delta y. So what would the distance be there? So using the Pythagorean theorem, that is just delta x squared plus delta y squared, right? Well, now what we do with calculus then is we look at that and we say, oh, you know what, that interval's too big and that approximation isn't quite what I want, so let me break it up into a bunch of smaller intervals. And I'm just going to draw two just so I have room to draw, okay? And now we have the change in x here, the change in y here, the change in x here, the change in y here. And now when we add those two together, all right, that would be a closer approximation. And then we keep breaking this interval up into smaller pieces, but we always have those rectangles that we're adding up. And when we're adding up an infinite number of things, that's an integral, right? Okay, so if we integrate with respect to x, look at what happens. Okay, we can take and if we multiply this by delta x squared and we divide each of these by that same thing. All right, so imagine if you use that distributive property, that's just the same thing I've written down, right? Because those delta x squareds would cancel out with what's in the fractions. Well, in that first case, well, isn't that just a 1 because we're dividing something by itself? In the second, we have delta y over delta x squared, and this is the square root of something squared, which is 2 times that. Now, I'm really not integrating anything here yet, okay? But now, when I think about all of those little sums, and that's our differential, this thing, the derivative of y with respect to x would just be f prime of x, right? So that's where that 1 comes from, okay? Now, with the multivariable stuff, it's exactly the same thing, except for what? If we have some kind of curve in here that goes around, okay, now we have to worry about, it meanders around a little bit in 3 different directions, and so the distance between there is the delta x squared plus the delta y squared plus the delta z squared, right? But we're still just using the Pythagorean theorem stuff. Now, the only difference this time is we're thinking about it like a parametric equation. I mean, look, okay, if we go back to this, I have this notation stuff is, y is a function of x. But if we were to write this as a parametric equation, that's the same thing as having x prime of t squared plus y prime of t squared. And using that as my interval, okay? And we differentiate with, respect to t. It's the exact same thing, but in one case we're looking at it as a parametric and the other one we're not. With these, with like the vector valued functions and stuff like that, it's a lot easier to look at it in terms of its parameters, but it's still just that Pythagorean theorem, in this case kind of used repeatedly. I don't know why I have that squared there since I have the square root. Okay? But our integral then is x prime of t squared plus y prime of t squared plus z prime of t squared, or whatever, dt. whatever letters you use to represent the different things. So maybe this will help explain the difference in those two a little bit.